Oh, hi! Looks like I'm live. Very good evening. How are you all? And like I always say, Namaskara everyone. Andariki Namaskaram, Ellargu Swagatam. This is me, your master teacher Nabamita Ma'am. And today we are doing this one very important chapter. Chemical bonding, believe me, is one of the most fundamentals of your chemistry, right? This chapter is not only related to your inorganic and physical, but also it is much required in your organic chemistry. So first of all, if you study this chapter properly, then 8 marks is guaranteed. Apart from that, you can also solve a lot of organic chemistry questions just from this chapter. So very good evening, guys. I hope that I am audible and I am visible clearly. You all know the rule of the class. What do you have to do every time you understand something and you think that this is an easy peasy explanation? You write hashtag EPBT. Yes, and quickly go and call up your friends, everybody, because we are going to start this chapter right away, right now, everyone, and we are going to complete it. Yes, so we have basically 2 to 3 hours and we are going to complete everything. We are also going to solve some questions, but not so much, because yesterday we did solve a lot of questions anyway, right? So quickly go and call up your friends, everybody. Let us begin this session without much further ado and without any disturbances. Okay, yes. Hi everybody. Hello bachos. Hello. No, I do not know any other language. I do not know Tamil, Telugu, Malayalam or Kannada. I know a little bit of Kannada, but that's it, right? I can only greet you in these languages, not much more than that. That's why I'm teaching you in English. Otherwise, I would have taught you in Telugu, right? So anyway, guys, before I start with the session, let me also give you the schedule of this week. Today is a Thursday and at 6 p.m. right here, right now, I am taking this chemical bonding session. After this, at 9 p.m. today, you will have Shreyas sir's session, which is at, which is current capacitors and AC PYQs. After that, tomorrow you will have Pahul sir's session at 6 p.m. reaction mechanisms and haloalkanes. And then tomorrow at 9 p.m. you will have sequence and series mathematics PYQ. So this is our schedule and we will update you after 29 December what we are going to do. So now everybody, are you all with me, guys? Are you all with me? Good evening, Manisha. Good evening. Looks like you are absolutely ready to go to IIT Madras, isn't it? So everybody, let us begin. What you all say. So let me give you a little bit of what do I say? Let me give you a little bit of basics, right? So we all know that we have already studied atomic structure long back, and we know that in atomic structure we have in the middle of the atom we have the nucleus and there are electrons which are revolving, right? And under normal conditions, we know that no element want to exist as an independent atom, because I mean, come on, we are also looking for stability, isn't it? We want to go to college, we want to go to office, and then after everything is done, we want to get settled, get married to someone. Why are we doing this? Because stability. Hey, these things are called as stability, isn't it? Just for the sake of stability, we go to college, we earn good money, we go to office, and then finally we settle down, right? Don't we do that? We do that. Yes. Similarly, atoms also do that, except noble gases. Now, looking at the noble gases, certain chemists or some scientists, they thought that, oh, if these guys are so stable, that means that they have something which is making them so stable. And what was it that was making them stable? It was that octet rule. They had 8 electrons in their valence shell, which was not allowing them to mingle with everybody, isn't it? Yes. And that's why they do not form any bonds. Now, coming to bond, everybody, let us talk about bonds here, everyone. So when we talk about bond, what is bond? What is a bond? A bond is nothing but just a mere force of attraction between the atoms. I have just told you that atoms, they want to combine, they want to form molecules. Why so? Because they want to attain stability. Why do they do that? Because they want to attain stability, which is why you will find them forming molecules. And while they are forming molecule, what are they doing? They're forming bonds, right? So initially, everybody, we are going to start with everyone. What? We are going to start with bonds, right? Bonds, you understand, everybody? Yes? Bonds, you understand. What are bonds? Bonds are basically, can you guys see me now? Hi, can you guys see me now? Now can you guys see me? Is it fine? You guys can see me, right? Everything is clear, crystal clear? Okay, now it's okay. Okay. So bond is the force of attraction between the atoms. That is done. Okay. Now, obviously, as we move forward in the basically the later part of the chapter, we will also learn about different types of bond. And I have already told you in the previous session, now bonds are of two types, right? Let us say that we have certain bonds which are called as strong bonds. And what are these strong bonds? These strong bonds, my dear students, are everybody, as you all know. Yes, the first one, the first strong bond. Anybody in the chart section who wants to tell me this? Yes, the strong bond here is a covalent bond, right? Covalent bond is a strong bond. Then what do you have? You have something called as a coordinate bond, right? Yes, apart from that, what other bond do you have? You also have something called as ionic bond. This is also strong, right? Ionic bond is also strong. Apart from that, what other bond do you have? You also have something called as metallic bond, guys. Yes, what do you have? You also have something called as metallic bond. So these are the strong bond. And then in the weak bonds, we will read about hydrogen bond and van der Waals forces. Of course, we will read them in detail. So right now, I am not getting into the detail, everybody. Yes, do we understand? Then now, after formation of bond, what happens? You get a molecule. And there are several molecular formation theories, right? And what are those? First, we get into Cossel-Lewis's approach. Yes, and that happened in the year of 1916, long back. Then we have VSEPR theory, which is basically nothing but valence shell electron pair repulsion theory. Then you get into VBT, that is valence bond theory. And finally, you get into molecular orbital theory, isn't it? Yes. Yes, everybody, great. Now, coming to Cossel-Lewis's approach. Yes, let us come to Cossel-Lewis's approach. But before that, let us talk about a little bit of octet rule. What is this octet rule, my dear student? Anybody wants to tell me what is this octet rule? Anybody wants to tell me octet rule? What is octet rule? Octet rule, it dictates that atoms are most stable when they have 8 electrons in their last shell. Got it? What did I say? I said that atoms are most stable. Atoms are most stable when they have 8 electrons in valence shell. Yes. Now, listen to me very carefully when I say this, that octet rule is not universal. Why so? Why is it not universal? I mean, come on, we know that noble gases are chemically inert. But hello, do we not know about xenon compounds? We do know about xenon compounds. That means that xenon is a noble gas and yet it is forming compound. That means that this is not absolutely true, that 8 electrons is something that is not allowing them to form bonds, right? That's not true. So yes, then we come to limitations of octet rule, and that's why we have this whole chapter, that is chemical bonding and molecular structure, right? Yes, so we come across limitations of octet rule. Yes, what do we come across? We come across limitations of octet rule, bachus, right? Now, what are the limitations of octet rule? First of all, everybody, we come across something called as incomplete octet. What is it? The first limitation is incomplete octet. What is it? Incomplete octet. Now, incomplete octet bole to, what do we mean by incomplete octet? Chalo, let me give you an example of BH3, right? We have BH3, everybody. Now, have a look that boron has how many? Boron has, everybody, 3 electrons in its outermost shell, right? Boron belongs to group 13. Group 13, what do you have? Bal Gangadhar Indian Tilak or Bangan Alu Gajar in Thali. Bal Gangadhar Indian Tilak, that is boron, aluminium, gallium, indium, thallium. This whole group, they have 3 electrons in their outermost shell, right? So that means that this boron is going to form 3 bonds here with hydrogen, and we all know that here basically what would have happened is 2 electron, 2 electron and 2 electron. So now if you want to calculate how many electrons are surrounding boron, have a look. It is still just 6 electron. Does it reach 8 electron? Does it reach 8 electron? Not at all. Not at all, my dear students. So can we say that this is what? Incomplete octet. This is incomplete octet. It is 2 electron less than 6 electrons. So this is your incomplete octet. Great. Moving on, now you also have something that is called as odd electron molecule. What do we have? We have something called as odd electron molecule. Now what is this odd electron molecule, everybody? Have a look. Let's say that we take example of NO. Yes, we have nitric oxide. What is this? This is nitric oxide, right? Now we all know that in case of nitrogen, how many electrons does nitrogen have in its outermost shell? Nitrogen has, my dear students, 5 electron in its outermost shell, right? 5 electron, bachu. So 5 electron, that means that, okay, let's say everybody, I'm just going to rub the oxygen from here and let me write it here. So now you see that nitrogen has 5 electron, right? Let's say that here it has formed a double bond and it is sharing 2 electrons here, lone pairs. So now do you see everybody that this particular molecule, this has odd electron, and this is also not able to fill its octet. Is it able to fill its octet? Everybody see, 1 2 3 4 5 6 7 7 electron only. Count the electrons that nitrogen has, everybody. Count the electron that nitrogen has. If you count it, you will be able to see. My dear students, do you see here? It has 1 2 3 4 5 6 7 7 electrons are only there with nitrogen. We still do not have 8 electrons. So do you understand the limitations now, everybody? Are we getting the limitations? Are we able to understand the limitation? It's not loading anymore, right? It's not loading anymore. I think it's fine. Guys, chat up. Chat up. Please talk to me. If you don't talk to me, I do not understand that if whatever I'm telling you, whatever I'm teaching you, is it clear or not clear? Yeah, so please keep chatting, everybody, and don't stop chatting. Yeah, everything is clear. This is clear. Do you understand this odd electron molecule and how we have come across this? Do we understand this odd electron molecule, everybody? Do we or not? Do we understand this? Clear? Yes. So shall we say EPBT? Shall we say EPBT? Odd electron molecule is clear, right? Yes. No problem. We will also solve. Don't worry about it. Chalo. Next, there is something that is called as, everybody, the next one is expanded or hypervalent octet. What is it? Expanded, or yes, what do you call it? Hypervalent. Okay. Hypervalent octet. So what do you mean by expanded or hypervalent octet? Yes, what do you mean by this? We mean to say, okay, let's have a look at it, everybody. Let's take the example of PF5, okay? PF5, everybody, and now have a look for PF5, everyone. Let me draw the structure here. So you have P and then 1 2 3 4 and 5, okay? 1 2 3 4 5. So you have F here, F here, F here and F here. Now count. 1 2 3 4 5 6 7 8 9 10 10. Oh, hello. What happened to octet rule? We thought there was only supposed to be 8 electrons, but here how many do we have? We have 10 electrons, my dear students. So after we have come across 3 limitations of octet rule, I think that's it. We are done. We are sorted. We were like, nah, we do not need this rule anymore. We do not need this rule anymore because this is not able to solve major concerns, right? So we have discarded this rule, and you have to understand that octet rule was completely based on the fact that chemical inertness of noble gases. Noble gases are chemically inert, and we also understand, but that xenon, however, forms compounds with oxygen and fluorine. So we get to see 4 limitations now, and that's it. We are done. So now we come across what Cossell and Lewis would have said. Please understand Cossell-Lewis's approach. I'm not going to write anything because it's a very simple, theory, and I do not think that you will be asked any questions in JEE Mains. In JEE Main, you will be asked question from hybridization, you will be asked question from VSEPR, VBT, and definitely molecular orbital theory. These 4 theories are very important. Now, getting back to Cossell-Lewis's approach, please understand that Cossell and Lewis, they were like, Acha, so we understand that it is only the outermost shell, right? It is only the outermost shell that are taking part, that are participating in a molecule formation, that are participating in the reaction, right? So how about let's call everything that is inside, let's call it as a kernel, and only the valence shell we will keep it, right? And that's when they say that, that's when what they did was, they were like, you know what, let us call everything else that is inside, all the penultimate shell, all the shells that are inside will be considered along with the nucleus as a kernel, and whatever is in the last shell, that we call it as valence shell, right? Then Lewis came up with something also called as Lewis dot structure. Do we know how to draw Lewis dot structure, everybody? Do we know how to draw Lewis dot structure? For example, let us take the example of Cl, right? Now, chlorine has how many electrons in the outermost shell? Chlorine belongs to group 17. Group 17, fluorine, chlorine, iodine, astatine, bromine, all of them have 7 electrons in their outermost shell, and 7 electrons will be drawn as 1, 2, 3, 4, 5, 6, and we're not here. 7 electrons. That's what I have indicated. Okay, that's exactly what I have indicated, right? So this is how you draw the Lewis dot structure. Great. Okay, understood. Any doubt here? Now, while you are drawing the Lewis dot rule, sun lo, listen to this, because this will also help you in your board exam. To all the students who are sitting for your 11th board exam, or in your or in any other board exam, this is important, so just listen to it. Now, Lewis dot rule is, whenever you are given a compound, if let's say you are given a compound and you are asked to make a Lewis dot structure, then the first thing that you do is, so there are basically 5 rules, right? 5 rules. First rule is that you count the total number of valence electron, okay? You count the total number of valence electron. Second rule is you identify the central atom, the one that is less electronegative. Like fluorine, if I give you IF7, right? If I give you IF7, you will tell me directly that, ma'am, iodine, I is the central atom, right? You are not going to tell me, ma'am, F7 is the central atom, because you understand that fluorine is more electronegative, right? So the one that is less electronegative is going to be your central atom. Then you draw the skeleton, then you join them by single bonds. You assign the remaining number of electrons as lone pair and convert the lone pair into double or triple bond. Then you complete the octet of all the atoms, right? Understanding, everybody? This is how you do it, okay? This is how you do it, okay? All right, everybody. Cool hai? Cool hai, cool hai, cool hai, cool hai, cool hai. Can I get some EPBT in the chat box, everyone? Can I get some EPBT in the chat box? Yes or no? Yes or no, everyone? Acha. Chalo, let me draw one structure for you and let me explain this to you. Let's say that we have CO2, let's take. Yeah. If we take CO2, so we know that carbon has 4 electrons in the outermost shell, right? Plus, we will have 2 multiplied with 6. So, we will be getting 4 plus 12 is equal to 16 electrons altogether. So, now let us draw C here. 1 here oxygen, 1 here oxygen, right? Now we will have, now we see that carbon is done with 2 electrons carbon has already shared, right? Okay. Now see, for oxygen we will have 1, 2, 3, 4 and 5, 6 here. 1, 2, 3, 4, 5, 6 here, right? What oxygen will do is these 2 electrons it will donate here. These 2 electrons it will donate here. Now finally our actual Lewis dot structure will look like, everybody, C double bond O like this, and then we will draw the remaining electrons as lone pair like this, and that's it. That's how you do it. Okay, that's how you do it. Got it? Clear? Yes, we have followed the exact same rule and we are done with it. Okay. All right. Now we come across something that is called as VSEPR theory. But before we do VSEPR theory, everybody, before we do VSEPR theory, I have to tell you something about formal charge and, wait a second. I have to tell you or teach you something about formal charge. Yes. Okay. One last page. Yeah, that's it. Sure. Now let us understand, Bachu, I am only explaining this initial part while I'm writing. After that, we will not write anymore, because understand that we have to finish this huge long chapter in just 3 hours. Okay, so we have to finish a lot of it, and that's why I'm not even talking to you more today. Yeah, you see that I'm not paying attention to the chat so much, because I need you all to pay attention and complete the chapter. So first of all, let us talk about the charge on ions. What do we understand by charge on ions, right? Yes, let us talk about charge on ions. Here we go. For charge on ions, everybody, for charge on ions, to understand charge on ions, let us take the example of CO3 2 minus. Now, how do we draw the structure of CO3 2 minus? You know what? We can draw the structure of CO3 2 minus as here, double bond O here, single bond O here, and another single bond O here. Yes, we can do this, right? We can do this, okay? All right, everybody. Now here I am writing here 2 minus. But is this the only structure that is possible? Not at all. This is not the only structure that is possible, because we know that this negative charge 2 minus that we have, this can actually go around the whole molecule and it can get stabilized. It can get stabilized, right, everybody? Yes, do we know this? We do know this. Now what will happen is, the second structure that we can draw, everyone, is, have a look, everybody. Guys, I hope that you all are paying attention. Yes, here the second structure that we can draw is, let's say that we have seen double bond O here, single bond O, and single bond O here, and here we can write 2 minus. This is not the only one. We have another structure that is possible here, and the last structure looks a little bit like this. Here, see, C double bond O here, single bond O, single bond O here, and finally we write here 2 minus. This is also possible, right? This is also possible. Now, while we're talking about charge on ions, we come across another term that is called as formal charge on ions. What is this formal charge on ions? What is this formal charge on ions, right? What is it? Okay, somebody has asked me, ma'am, why double bond? But here, see, there are 3 oxygen atoms and there is 2 negative, right? 2 negative. Where will this 2 negative charge go? These 2 negative charge will actually be, taken by the 2 oxygen and 1 oxygen which is neutral, which does not have a charge, that is going to form a double bond. So what will happen is, this negative charge, when it comes here, this charge will go here, right? This charge, this double bond will break and it will go here. So this resonance keeps happening, which is why you get so many structures, and obviously none of them exist because we call them as canonical form. What exists is the resonance hybrid of these structures. We will come there as well, don't worry about it, but I hope this is clear. Now, I have just told you that we come across a different term that is called as formal charge on ions. Okay, we come across formal charge on ions. And what is a formal charge on ion? The formal charge on ion, everybody, is, you have to understand, it is the difference between the number of valence electrons of that atom in an isolated or free state and the number of electrons assigned to that atom in the Lewis structure. Didn't understand? Let me write it again. It's there in your NCERT as well. Let me write it. I think then you will be able to understand. What did I say? I said total number of valence electron. What did I say? Total, 1 second. Sorry, my charge is gone. I said one. Everybody listen to me. Formal charge is total number of valence electrons in free atom minus total number of lone pair electrons minus half of total number of bond pair electron. Why half of bond pair electron? Why half of bond pair electron? Because understand this, bacha, bond pair, when I'm forming this bond, I am giving one electron. The other atom which is forming a bond with me, they are also giving me one electron. Hence, half of bond pair electrons. Gotcha? Yes. So let us write that down now. What did I say? I said that total number of, okay, total number of valence electrons, total number of valence electrons in free atom or free state, yes, in free atom or free state minus total number of lone pair, okay, total number of lone pair electrons minus half of total number of bond pair electrons. Okay, I will just move aside. Everybody please have a look and tell me now, do you understand what is formal charge? You will write down the total number of electrons in free state, then you will subtract total number of lone pair of electrons minus half of total number of bond pair electron. Is this easy peasy clear, everybody? Is this clear, guys? Is this clear, everybody? Just have a look and tell me that this is understandable or not, everyone. And please write down hashtag EPBT if you have understood. Come on, guys. Come on. Quick. Everybody, do we understand this? Do we understand this? Yes. Right? Okay. Clear? Shall we move on then? Shall we move on? Is formal charge clear? Formal charge is clear, everyone? Yes? Very good. Okay. Now, moving on, let us understand something that is called as, let us understand one of the bonds. Okay. Let us understand ionic bond. How does this ionic bond formation take place, right? Ionic bond formation. Acha, to form ionic bond, for example, let's take the easiest example that is available for us, that is NaCl, right? What happens? In NaCl, we see that one electron moves from sodium's head to Cl head, right? Yes, everybody. Ionic bond, for example, okay. Let's say that Lakshita and Trishaya, okay? Lakshita and Trisha, sorry. Lakshita and Trisha are in my class, okay? Lakshita and Trisha are in my class, and I have given you an assignment and I have told you that, bachus, you have to write the question with black pen, answer with blue pen. Now, Lakshita had, okay? Now, Lakshita had blue pen and Trisha had black pen, okay? Lakshita had blue pen and Trisha had black pen. What they have done is, Lakshita has given her blue pen completely. After writing all the answers, Lakshita has given her blue pen completely to Trisha. And Trisha, after writing all the question, has given her black pen to Lakshita. So do you understand? Like a complete transfer has happened. Transfer of the valence electron has happened from one atom to another. Now, for this to happen, everybody, there are 3 or 4 factors that are in picture. And what are these 3 or 4 factors, right? What are these 3 or 4 factors that we have, everybody? So understand that first of all, you will require ionization enthalpy. Why do you need ionization enthalpy? Because, hello, you need to take away one electron from the atom, and if you want to take away electron from the atom will be like what? So forever happy, like ha, lelo, take away, take it, just take it and go, just take it and go. Will atom do that? No. The atom is going to ask you for some energy. Yes, for example, you know, I keep giving you examples of me being a shopaholic, that I like shopping, right? So I love shopping, isn't it? Every girl likes it. Come on, yeah, don't judge me, but understand that I like shopping. Now, if I just go to Myntra and I think that I want to buy sweaters because it's winter, will Myntra give me free of cost ka sweaters? Huh? Myntra is like what? My uncle, that they will just give me free of cost sweaters. They'll be like, yeah, Nabamita Ma'am, why not? You teach so many students, take it and go. No, I will definitely have to spend some money. That's my currency. But in case of an atom, their currency is energy. Yes. So you have to provide some energy to take away the electron, and that, my dear student, is your ionization enthalpy. Then comes that, acha, now Mintra is giving you discount and discount, right? You know, you have all those sales, all those sale, right? Big Billion Day and what is it in Amazon? Great Indian Sale Festivals, so, sort of these kind of festivals that you have. Okay, so now if they are providing you with the sale, the consumer also has to be there, no? If I say that I don't want it, why are you giving me so many discounts? Why are you giving me? I don't want it. Then what will happen? There is no consumer, so then they will stop giving you this discount. So you are understanding. So if sodium is absolutely excited to give away one electron, the chlorine atom also has to be acceptable. The chlorine atom also must think that yeah, I will take that electron if you give me. That is called as electron gain enthalpy. What is this? This is called as electron gain enthalpy. When an electron is accepted by the atom, it releases energy, which is what chlorine does. Yes, so here, do you understand ionization enthalpy and electron gain enthalpy? Two things I have explained to you. And finally, we come across something called as lattice enthalpy. What is this lattice enthalpy? Now you have understood that after giving ionization enthalpy Na, sodium has released one electron, and after releasing some energy, chlorine has taken the electron and they have formed a bond together. Now, the lattice enthalpy is how much energy do I require to break them? How much energy do I require to break them? That is called as lattice enthalpy. And in a little bit of chemistry funda, let's understand that the energy required to separate 1 mole of solid NaCl into 1 mole of Na plus gaseous state and Cl minus gaseous state, that is called as your lattice enthalpy. Yes, everybody, do we understand this? Is it clear? So ionic bonds, when will they form very easily? Yes, for a stable ionic bond, to be formed, we require 2-3 things. What are the things that I've told you? I've told you that low ionization enthalpy. That's the first thing, okay? The atom should be easily agreeing to give away one electron. Yes, the atom should be easily available or easily happily ready to give away one electron. Yes, then we have high negative electron gain enthalpy. Okay, high negative electron gain enthalpy. What do we mean by high negative electron gain enthalpy? That means, for example, the chlorine atom should be readily agreeing to take that one electron that it is coming, right? That is coming across its way, right? And finally, we also want high negative value of lattice enthalpy. What do we want? We want high negative value of lattice enthalpy. All right, everybody. Yes. So these are the 3 things that we require if we want a stable ionic compound. Okay. If we want a stable ionic compound. All right, everybody. This is clear, guys. This is clear. This is clear. Yes. All right, everyone. Great. Now let us go ahead and let us understand VSEPR theory. Everybody, are you all with me? Shall we do that? Shall we do that? Yes. Very good, Rimpi. Very good. Hi, Radhe. Hi, Manisha. Hi, Ibrahim. Yes, you are a little bit late to the class, but no worries. No worries. It's okay. It's okay. We will be able to do it. Chalo. Chalo. So let us start with VSEPR theory. Right? Now, valence shell electron pair repulsion theory. That's our VSEPR theory. Before this, was there anything else that I had to teach you? We had to talk about bond parameters and all of that, but I guess we will talk about bond parameters and all of this later. And also we will talk about Fayon's rule at the end of the session. Okay, don't worry. Sure. Now let's talk about VSEPR theory. Now you all know the full form of VSEPR theory. What is it? The full form of VSEPR is, what is it? It's valence shell electron pair repulsion theory. That means that, what does it mean? Actually, the answer is there in the heading itself. The heading says that there should be minimum repulsion between pair of electrons at valence shell. So at the last shell, if there are pair of electrons that are available, those pair of electrons must have a minimum repulsion. That's it. Now coming to the question that, ma'am, why do we need another theory, ma'am? Why did we do that, ma'am? Why did we need another theory? Was it not enough that we already had Causal-Lewis's approach? We already had octet rule? No, it was not possible, because we saw that Lewis structure could not explain the shape of molecules, right? We did not. And that is why we needed this. Now in VSEPR theory, there are certain postulates. Postulate number 1 is that the shape of molecule actually depends on, what does it depend on? Oh, I forgot. The shape of molecule depends upon the number of valence shell electron pair around the central atom. Okay? Yes. How many number of valence shell electron pairs? That means how many number of lone pairs are there. Based on that, the shape depends. Yes. And we will also understand the difference between shape and geometry. Geometry is from hybridization and shape is without the lone pair. What shape do you see? That is what is your shape. Okay? Postulate number 2 that VSEPR talks about is, the postulate number 2 was valence shell electron pair, they occupy such position in space so that the repulsion is the minimum and they are stable. But you understand, right? Acha chalo. See, for example, I'll give you an example, right? Me and my brother, we fight a lot. Me and my brother, we still fight a lot, even today. Even today, if I go home, when I go to meet my parents, right? And he stays with my parents, obviously. And we know that each and every time I go home, we fight. Now, our parents have made it kind of their duty that, so these two, right, these two brother and sister, our rooms are in such a way that it's close, but it's also far away. It's also far away. So if there is, let's say, my room is right here, then the next room is actually my parents. And after that, you have to walk a little and then somewhere is my brother's room. So they made it a point that, acha, this is bond pair, this is bond pair, but these two, the repulsion has to be minimum. So we do not come across, so we do not see each other all the time, and we don't go on like, fight. So this repulsion, to make sure that the repulsion is minimum, they make sure that our rooms are far away. So you understand, this is exactly what valence bond is talking about, right? Yes, now you have to understand that this theory right here, everybody, have a look what it says, right? This theory right here, it predicts the shape of the molecule by doing what? By considering the most stable configuration of the bond angles in the molecule. And it also states, what does it state? It states that electron pairs in the valence shell of the central atom of a molecule, doesn't matter if it is bonding or lone pairs, are regarded as occupying localized orbits. Okay, and these orbitals, what do? They arrange themselves in the space in such a way that they minimize the mutual electronic repulsion. What is this mutual electronic repulsion? Let us try to understand this, bacha. Okay, for example, let's say that we have two hydrogen atoms. Okay, so let's say that we have one S here and we have one S here. Okay, yes. Now imagine what is happening is, let's say, okay, let's say that this one wants to come closer. Okay, when this is coming closer, everybody try to understand, when this is coming closer, let's say that it has come here. Okay, now that it has come here you have a nucleus, here you have a nucleus, here also you have a nucleus. This nucleus is going to pull the electron like this nucleus is going to pull the electron like this, but this electron and this electron will also repel each other. This repulsion has to be minimized. This repulsion has to be minimum. Are you getting my point, everybody? Are you getting my point? So this mutual electronic repulsion that is happening, that has to be minimum, right? Now what happens is, there is a what do you say? There is a I'm forgetting the English word. What do you call it? Basically, the repulsion is maximum and minimum where? Let's talk about that. So you see, A lone pair. Okay, understand. What is a lone pair? What is a lone pair? A lone pair is a free bird. The lone pair is not bonded with anybody. The lone pair is not bonded anybody. Okay, another example. Story time, everybody. Have you noticed that if you stay in a society, for example, let's say that you have an apartment society or some sort of thing, you know, these apartment society people, yeah, this apartment society people, or there are certain owners, they will be like, I do not want to give my flat to bachelors. Why? Because bachelors the bachelors, they're free bird, they're not bonded, and hence they want to, you know, what they do is they usually dirty the house, they do not take care of the house, they break a lot of things, and that is why the owners, they're like, no, I don't want to give it to the bachelors, I don't want to give it to the bachelors. They prefer giving it to the families because families are bonded, they will stay together, there will not be much of kalesh, fight, whatever, right? That is why. So this lone pair, they are just on top of one single atom. Yes, they're on the head of the atom, they are localized. The lone pair is localized, hence it needs more space. It's like मैं तो फैल के बैठेगा. I will spread and sit like this. Yeah, I will spread and sit like this. I don't want to sit like this, you know. I want to take more space. So lone pair repulsion is maximum. Then it comes to lone pair, bond pair, and finally you get to bond pair, bond pair. The bond pair are already bonded, right? So they're like, apne ko kya hai? How does it matter to me? I am fine. I am bonded already. I don't want to repel so much, right? I don't want to repel so much. So they're fine. So you understand what is happening here. Have a look, everybody. This lone pair and lone pair, they are going to repel each other a little more. This lone pair and bond pair, this repulsion will be a little less, and the bond pair and the bond pair will repel even less. Somebody is asking me, ma'am, what is repulsion? Anmol, do you have something called as dictionary? Have a look at that. Because this is not chemistry. Have a look at the dictionary, you will find it, okay? Chalo guys, moving on. Now we understand that the electronic repulsion between two pairs of electrons, it will be minimum if they are far apart as possible. I mean, that's exactly what I told you. That's exactly what I told you, isn't it? I have just told you that only. What did my parents do? My parents made sure that my brother and I, our rooms are so far away that we talk but we don't fight. Right? That we talk but we don't fight. So that, my dear student, is what is your VSEPR theory. Gotcha, clear? Okay, now the actual shape of the molecules which contain lone pair is a little distorted. I have just told you, if there is a lone pair, the lone pair would want to, you know, chill and sit like this. So it will take more space. It will take more space. So what happens is the shape, the actual shape of the molecule becomes a little distorted from the basic shape, as in the NH3 and H2O molecules. In case of H2O, what happens is, see, have a look, everybody. In case of H2O, chalo, let me move this side and see. See, hydrogen is forming a bond pair with oxygen. This hydrogen is once again forming a bond pair with oxygen. But what is the number of electrons in the last shell of oxygen, everybody? Oxygen has 6 electrons, isn't it? Oxygen has 6 electrons in the last shell. So that means that oxygen still has 1, 2 and 3, 4 here. And because of this, what is happening is this one is pushing this bond pair, this one is pushing this bond pair, and these two are also pushing each other. Hence, you see that although this is supposed to be a tetrahedral shape, but you still have a bent shape here. Yes, what do you see? You have a bent shape here. The shape changes. The shape gets distorted a little bit. Okay, the shape gets distorted a little bit. And here the bond angle was actually supposed to be 109 degree 28 minutes. But it's not. It got distorted. See, because the bond pair was pushing it and pushing it and pushing it. So what happens is, in case of water, it becomes 104.5 degree, and in case of NH3, you get to see that it is only 107 degree. Am I making sense, guys? Hey, oxygen has 7 electron. Anmol bacha, which class do you belong to? Please don't do that. These students, they are going for their JEE exam. If you do all of these, they're going to be super confused. Yes, oxygen belongs to group 16. It has 6 electrons in the outermost shell. Also, you will make me forget my chemistry if you write these kind of things. Please don't do that. Chalo guys, yes, order of repulsive interaction we have already understood. Lone pair, then lone pair, bond pair, and then finally bond pair, right? Yes, we have understood all of these. Great. Acha. Now, yesterday somebody was asking me. Yesterday, one of my students, they were asking me, ma'am, how to draw the shapes? How to draw the shapes, ma'am? How to draw the shapes? Yes. So, how can you predict the geometrical shapes? How can we predict geometrical shapes? Let's talk about that. And while we are talking about how to predict geometrical shapes, I think it will be better if, in case, according to VSEPR theory, if we divide the molecules into two groups. One will be where there are the no lone pair. That means the central atom, if it does not have any lone pair, one will be that group. And the second group will be where we have one or more lone pair. So now everybody, are you all ready with a pen and paper? Because we are going to solve a lot of questions now. Yes? Chalo. We are going to solve a lot of questions, everybody. So are you all ready, guys? Are you all ready? Are you all with me? Are you all with me? Are you all with me? Come on, guys. Everybody, you with me? Chalo. Now let us say, now we are going to take a look at, please read the heading. The heading says geometry in which the central atom has no lone pair. In this case, what is it? Geometry in which the central atom has no lone pair. Okay, no lone pair. Is this clear? Have we all understood that this has no lone pair? Now, let us understand that, let's say that we have electron pair 2. If you have electron pair 2, okay, if you have electron pair 2, that means that the molecule is, let's say, AB2 type. AB2 type. So your central atom will be here A, and you will have a B here, you will have a B here, and this A is going to give you 1 electron, B is going to give you 1 electron. Similarly, this A is going to give you 1 electron, B is going to give you 1 electron, and they're going to form a bond. And here, what is the bond angle? The bond angle, my dear students, you can clearly see that it is 180 degree, because it's linear, na baba? So linear, if it is linear, what will happen? 180 degree, right? That you have learned in your mathematics, isn't it? So what is the molecular geometry? The molecular geometry is linear. Yes, the molecular geometry is linear. Now suppose I want to take an example, right? Suppose we want to have a look at BeCl2. What did I say? The molecule type, everybody, I have just told you that the molecule type is AB2. AB2 bole to, can you think of any example? I've just told you BeCl2. What is it? BeCl2. If it is BeCl2, how am I going to draw the structure? It will be very simple. Be here. I will draw Cl here. Cl here. This angle is going to be 180 degree, right? So what am I going to write? If they ask me in the exam that theta is equal to 180 degree. Lo and behold. Can I have some hashtag EPBT? Can I have some hashtag EPBT? Acha. Now, something that is very important here is, everybody, try to understand. Again, look at the heading. The heading says, this case, the central atom has no lone pair. If there is no lone pair, then the geometry is going to be equal to the shape. Then the shape and the geometry are same, right? Then the shape and the geometry are going to be same. But you will see that when there is lone pair that exists, the shape and the geometry are not same. The shape and the geometry are not same. But here the shape and the geometry are going to be same. Pakka makes sense, everybody? Make sense or nonsense? Make sense, nonsense, guys? Quickly tell me, quickly. Go ahead, everybody. I need your answers. Yes. Do we understand? Here, because there are no lone pair, the molecular geometry and the shape are going to be same pinch. Same. Okay? Chalo, moving on, let's say that we have number of electron pairs 3. If we have 3 electron pair, any example that you come across, we have here BF3. How do we draw BF3? How do we draw BF3, everybody? Yes, how do we draw BF3? Very simple, very easy. See, I'm going to draw BF3 here. B here. Yes, and boron has 3 electrons in its outermost shell, isn't it? Boron has 3 electrons in its outermost shell. So 1, 2, 3. Simple, easy peasy. Yes, simple, easy peasy. So this, now if you let's say that if you just join this, right? If you just join this, what does it look like? What does it look like? All of this is on the same plane. We call this trigonal planar. What is this? What is this geometry? This geometry is called trigonal planar. Acha. Now, in mathematics, you have learned in a triangle, what is the angle that you are making here? In this case, the bond angle are going to be theta is equal to 120 degree. Make it sense with everybody? Make it sense it? Make sense, nonsense? Very good. Very good. Well done. Now, if there are number of electron pairs 4, if you have 4 number of electrons, then what are you going to do? Let's say, for example, you have CH4. Okay, how are we going to draw it? So, you have carbon here, 1 carbon in the middle. Similarly, similar to this BF3, we will put this 3H at the bottom here, and this 1H, we will keep it right on top of the head like this. Okay. Now, if we try to join this, what does this look like? What does this look like, bachos? This looks like a tetrahedron, right? It's like a 3D triangle, isn't it? It looks like a 3D triangle, so we call this to be as tetrahedron. Once again, is this clear? If it is clear, what do you write down? Hashtag EPBT, everybody. Yes? Yes. Are we done? Very good. I am super happy to see that you guys are also answering me in the chat box. Well done. Chalo, moving on. We still do not have any lone pair, guys. Still there is no lone pair. Look at this. Geometry in which the central atom has no lone pair. There is no lone pair. Okay. Now we have 5 number of electron pair. If we have 5 number of electron pair, then what do we have? We have PCl5. Let us draw the structure of PCl5, everybody. PCl5. So we have here, P here is there. Okay. Phosphorus belongs to nitrogen family. Nitrogen family has how many electrons in the outermost shell? 5, na? 5, right? If it is 5, then what do we have? 1. Yes. Then what do we have? We're going to have trigonal bipyramidal. So we will have a triangle here. And we will have pyramidal here. So Cl, 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 Cl and Cl. Now understand this, everybody. Have a look. See, this forms a triangle. So we call this trigonal. But apart from this here, see, this is going up like this. So this becomes like a pyramid and this becomes like a pyramid. You get my point, right? You get my point. Wait a second. I think I did have a... Yeah. So imagine this is basically your PCl5, right? This is basically your PCl5. So here, see, right here you have a triangle. And see, on the top you have a pyramid structure. At the bottom you have a pyramid structure. So what is happening? Bipyramidal, because there are 2 pyramid, one on the top, one at the bottom. So 2 pyramids, hence bipyramidal. And right here you have a triangle. So trigonal bipyramidal. Make it sense with everybody. Do we understand? Is this hashtag EPBT or not? We get it. Chalo. Next we have number of electron pair, let's say is 6. Then what will happen? If it is 6, there is no lone pair. Then what will happen? 1, 2, 3, 4, 5 and 6. Together all of this will become what? Octahedral. Yes, this will be octahedral. Have a look at the structure, everybody. Let's say that we have SF6. If we take SF6, then you will have 1, 2, 3, 4, 5 and 6, right? I did this. So F, F, F and F and F here. So this will become octahedral. This will show you octahedral shape. So this was all over, everybody. Together, all of this was no lone pair of electron. There was no lone pair of electron. Yes, my dear student, are we clear with this? This is clear to you all? Is this clear to you all? This is clear? Great. Now, let us go and understand. Let us go and understand, everybody. What if there is a lone pair? If there is a lone pair, then what do we do? Then what do we do? Huh? What do we do if there is a lone pair? Any idea? What if there is a lone pair? Then what are we going to do? Clear hai? ठीक है. All right, guys. All of this is clear, no? All of this is absolutely clear, right? Yeah. Okay. Chalo. Now let's talk about what if there is a lone pair. Okay. Let's move a little bit. Everybody. Here. Let us talk about if they have a lone pair. Oh, acha, one more. Last one left. Sorry. Last one left. What if there are number of electron pairs? 7. If there is 7, then this will form, see, IF7, everybody. This is your IF7 and this is going to be the geometry. So what is this geometry, everybody? What is this geometry called as? Anybody? I don't have the name written, so there will not be any cheating. Now tell me, IF7 will have what molecular geometry? What will be the molecular geometry of IF7? So you will be drawing here one I here, then 1, 2, 3, 4, 5, 6, 7, right? F, 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 F. How does it look like? This looks like, very good, Rekha, very good. This will be pentagonal bipyramidal. What will this be? This will be pentagonal bipyramidal. Okay, pentagonal bipyramidal. Very good. You guys are going to ace the paper, looks like. Chalo. Now let us talk about what if there is, what will be the geometry and what will be the shape if the central atom now has one or more lone pair. If the central atom now has one or more lone pair, then what do we do? Okay, then what do we do? Chalo. So now I am going to need some paper. Wait a second, guys. I need extra paper. This we have copied. Okay. Yes. Chalo. Let us start, guys. Yes. Let us start. Here in this case, okay, here in this case, have a look. So we have, let's say, a molecule which is of the type AB2E. What do we mean by AB2E? So that means that we have 2 bond pair and 1 lone pair. What do we have? We have 2 bond pair and 1 lone pair. Actually, you know what? Before this, shall I teach you what is hybridization? VSEPR theory you are all clear with, right? You have all understood now what is VSEPR theory. Everybody has understood. Now, before we get into this whole lone pair, bond pair and, a little more, let us understand first what is hybridization. Let's understand hybridization. After that, we will come to it because then it will be easier for you to understand the shape. Okay? So, let us start talking about hybridization. Hybridization, everybody. For hybridization, I think the easiest example that we can take is obviously CH4, okay? Let's talk about CH4. Now, in case of carbon, CH4, right? What do we have? We have, let's say, we have carbon here and we have 4 hydrogen, right? Now, we know that how does carbon's orbital look like? Carbon has 1s2, obviously. Let's forget about 1s2, but carbon has 2s here and 2p here, right? So we have 2s and 2p. Now we know that carbon's electronic configuration is 1s2, 2s2 and 2p2, correct? Everybody? What is it? Carbon's electronic configuration, my dear student, is 1s2, 2s2 and 2p2. Am I right? Am I right, bachos? Yes, yes, everybody, great. So that means you will have 1, 2, 3 and 4. है ना? Is what happens. Here is what happens. You see that the 2s and here you have 2p, right? So this electron gets transferred here and you will have one electron and each of the orbital. What do you have? You have one electron in each of the orbital. Now what happens? The hydrogen, all the 4 hydrogen, right? All the 4 hydrogen, they come and they see that, aha, empty orbitals. So the hydrogen, they come and they put their electron and then they form the bond. Here what carbon did was, when carbon excited itself, it excited itself, and you see that it transferred one electron from the s orbital to the p orbital. How did it do so? We all know that the 2s and the 2p orbitals obviously are not absolutely same when it comes to energy, right? 2s and 2p orbital are not exactly same energy level, but they are almost similar. So carbon, while it is exciting itself, it hybridizes, it brings them together, hybridizes, mixes them together, and then it gives it to the hydrogen that yes, come and put your electrons here. Come and put your electrons here, right? This is what happens. So what is hybridization? Hybridization is basically intermixing of pure atomic orbitals. Which was your pure atomic orbital? Your pure atomic orbital was 2s and 2p. So you intermixed the pure atomic orbital, right? And then you produced new hybrid orbitals specifically just for the bonding. See, understand it this way, everybody. Let's understand it this way. Let's say that, okay? Let's say that now, let's say that, okay, let's say, this is very easy, right? This is very easy. So let's say that Shreya sir and Namrata ma'am are coming to my house. Okay, let us take this example. Let's say that Shreya sir and Namrata ma'am are coming to my house. Now I have just let's say 1 cup of milk left and I have 1 ice cream. Now, if I give Namrata ma'am 1 ice cream, then Shreya sir will be like, "Arey, Nabamita ma'am is very weird. Why didn't she?" And I cannot give 1 glass of milk to somebody, right? If guests are coming, can I give them one glass of milk? It will be so weird, right? Yes. So now I was like, what do I do? What do I do? What do I do? Idea. What I did was, I took the milk, I mixed a little bit of, ice in it, and I took the ice cream in it, and I made a milkshake out of it. Let's say that the ice cream was chocolate milkshake. So what I did was, now I have mixed it all together. I made milkshake, and now when I give it to Shreya sir and Namrata ma'am, both of them are very happy and they're like, "Oh, Nabamita ma'am is such an amazing host. She gave us milkshakes." I mean, that's a great thing, isn't it? That's a very, it's a very, what do you say, very posh to have milkshake and everything in guest house, right? It's nothing that is, it's nothing that is like, everybody does it. Everybody gives you what, tea and coffee. I'm getting you milkshake, isn't it? Yes, I'm getting you milkshake. I mean, isn't that great? But now what happened was, so I took 1 glass of milk and 1 ice cream, and one here we got 2 hybrid milkshake glasses. Does that make sense to you, everybody? Does that make sense to you? So here also, this is what happened. Yes, we mixed it up, and then we get, so there were 1 2s orbital, 3 2p orbital. Together they formed 4 hybrid orbitals. They formed 4 hybrid orbitals, and from there, that's how we form the bonds, everybody. Okay, that's how the bond formation and everything happens. Is this clear, guys? Yes. With this example, I hope that you all know now that Shreya sir and Namrata ma'am, whenever they come to my house, I believe they are going to have some chocolate milkshake here, okay? Do let them know in their sessions that Nabamita ma'am has told that they will get what? They will get milkshakes when they come to my house, okay? They will get milkshake when they come to my house. Do let them know in their session. At 9 p.m. Shreya sir has a session, right? Do let him know. Chalo. Now guys, let us understand that what and how do we calculate the state of hybridization. You know, this sp hybridization, sp2 hybridization, sp3, sp3d, all of this hybridization that we come across, how does that happen? Chalo, let us have a look at it. Let's make a table, everyone. Okay, let's make a table. So here, let me write here steric number. What is this? This is your steric number. Okay, after steric number here, now we will see orbitals participating. What is this? Orbitals participating. All right. And finally, here we have the geometry. Here we have the geometry. Cool. All right, everybody. So this is a table that we have made. Now, let's say that our steric number, acha, by the way, one more thing is, how do you calculate steric number? Steric number, when you calculate steric number, you always calculate it as number of lone pairs, LP, plus surrounding atom. How many atoms are surrounding the central atom? That together will give you the, very good, yes. So everybody has their different way of teaching, right? So when my teacher was teaching, he has always told us that number of lone pairs plus surrounding atom. Number of surrounding atom plus lone pair will give you steric number. Chalo, let's see that. My inorganic and physical chemistry teacher, his name was Rakesh Joshi sir in our school, and my tuition teacher was, what was his name? His name was, we used to call him Gupta sir, Gupta sir. Now I don't remember what his name was. It was Gupta sir. So both Gupta sir and Joshi sir has taught us like this. So now I'm going to tell you, everybody, have a look. So lone pair plus surrounding atom. Okay, lone pair plus surrounding atom will give you steric number. Okay. So let's say that our steric number is 2. If steric number is 2, bachos, then what will happen? If steric number is 2, then what will happen? Any idea? What will happen, bachos? What will happen? Anybody, everybody, tell me, what will happen? If steric number is 2, that means you have to understand that the orbitals that are taking part are, there is one s orbital definitely plus one p orbital, right? And that will give you what? sp hybridization. If it is sp hybridization, we have just seen, remember, what will be the geometry? The geometry will be linear. The geometry will be linear. Very good, very good, very good. Okay. All right, everybody, great. Now, let's say that our steric number is 3. If steric number is 3, that means there will be one s orbital and there will be two p orbitals taking part. That means that the hybridization is going to be sp2 hybridization. Yes. And our geometry will be what? Our geometry will be trigonal planar. What will it be? Trigonal planar, everybody. Yes, is that right? Very good. If our steric number is 4, then what do we say? We are going to say that we will have 1s plus 3p orbitals. Hence, we will get sp3 hybridization, and that means that this will be tetrahedral. This will be tetrahedral. Right, everybody? Yes, 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 yes. Great, amazing. Now, if we